So, welcome to week 6 of Electrical Machines 2 course. We just swap the screen and start our discussion. So, last week we discussed a very important concepts on the induction machines, slip concepts, and speed concepts, and also rotating magnetic field concepts. So, taking those key points together for today's starting point, I won't be writing all the key points which we have noted down at the end of last week's session, but I'll be picking up two important points out of those speed and slip discussions that will be needed for today's discussion. So, to start with today's discussion, we are currently discussing the concepts of induction motors, but today specifically we will be concentrating on equivalent circuit of three-phase induction machine. So per phase equivalent circuit we will be looking, and the same is applicable for the three-phase circuit. So the concepts and methodologies for per phase remain same even if you go for three-phase. So understanding a per phase induction machine is actually can be applicable for the three phase as well. Now, let's see two important points which I want to take further for today's discussion. That is, first one is the slip discussion. So, let me just write the today's concept which we are looking at is. So yeah, I was starting our session with the concept of equivalent circuit of three-phase induction machine. So the important key concepts which will be required for this equivalent circuit are in the last week, which we had a key points which we had noted down at the end of the session. Those are about the speed formulas and also a little bit about the slip also we discussed. So the main required points I'm writing it here, not all the formulas. I hope you remember them, but the important concept of slip and some initial discussion on the EMF and also slip I'll note down here, which will be the starting point to this week's discussion. I request students to mute themselves so that there won't be any disturbance. Thank you. So yeah, first one is about the slip I want to talk about. Yeah, when in an induction machine, since the rotor uh, rotates with some speed, an r, which is not the synchronous speed, so there will always be some slip existing in the induction machine. Now that we have discussed last week in detail. Now, if I want to write the formula of slip, this is equals to, yeah, I hope you remember this. Now, where the ns here, it is nothing but the mechanical rotations per second. That is, this is one of the formula which we have wrote the last week. I'm writing it again here. So this is in mechanical RPS. Now, 2F by P, F is the supply frequency and also P is number of poles of the machine. Now, the value of this slip will have a range. It will vary between two values. So what are those two values? What is the range of the slip? What are the minimum value and the maximum value? Let's consider in the induction motor case, right? So it might vary between 0 to 1. So between these two values, any value the slip can be. Now, what are the conditions we will say when the slip is having these two extreme conditions? When S is equals to 1 and when S is equals to 0. So what do we say about these two conditions? Okay. Now see, S is equals to 1 if you see. Now when will this S is equals to 1 happen? Anyone? Anyone have any idea? You can just see when will this S will be equals to 1, at what condition you can say N is equals to S is equals to 1.
Stand still, sir.
Yeah, exactly. Standstill condition. It means that there is no movement in the rotor. If you lock the rotor from movement, so there will be no rotor movement. Then there will be no NR. Speed of rotor is equals to 0. Now NR is equals to 0 means if you substitute NR is equal to 0 here, NS by NS, S will be 1. So S will be 1. We are calling that condition as a standstill condition, or I can also, it's a locked rotor in simple terms. Locked rotor condition. I can say NR is equals to 0 just to understand what is conditions. Now the other condition, S is equals to 0, 0 slip condition. Now this is, I would say this is not an ideal condition, because in if you remember the last week's one of the problem we have solved, that is about the no load condition in the in the machine. So when there is no load, that means if you take the shaft of the motor, there should be some load we will connect so that the machine will drive that load. Now, when there is no load and there is no opposing forces, yeah, there is no opposing forces means there won't be any opposing torque produced, not even friction. Friction will also be absent. So, in that condition, you would say Ns is equals to Nr. Right, there is no load on the rotor and there is no friction, there is nothing opposing forces on the rotor. Ns is equals to Nr, then Ns minus Nr will be 0 and slip is equals to 0. So that is not ideal, because under no load condition also friction will always be there. That is practical condition. So that's why we call this condition as a not so ideal condition, because in S equals to 0 means there are no opposing forces, no opposing torques, friction is equals to 0. So yeah, this is not so ideal. I also writing that not ideal, but I'm just saying I'm just discussing the possibility of these two conditions. Now I can also rewrite this nr is equals to 1 minus s into ns. So this is one topic which I want to start the discussion with, that will be useful for our further discussions. And the second point is induced voltage, induced EMF equation we have discussed last week. That is root 2 pi f kp kd phi and turns. So that concept also, it will be very much useful in equivalent circuit of the three-phase induction machine concepts, because the voltage induced in stator side and also rotor side, how we are arriving at the equivalent circuit. So everything is useful if you understand this. So I will be discussing that also. Stator induced EMF. Now I would call it as E1 because representing the stator side. The formula is root 2 times pi f flux phi per pole and kw1 and n1. See, now the kw1 here is the winding factor of the first side. So now we discussed in detail the derivation of winding factor, that is kw is nothing but the product of kp and kd, where kp is the pitch factor and kd is the distribution factor. Now when we multiply this kw window factor with the n1 turn, n1 that is the turns in the stator side, it will be as a effective turns that will be useful for your like that will be useful actually in producing the flux and all, because you know because of the pitching and because of the distribution, you might not be utilizing all the coils effectively. So the voltage produced will be less than the full maximum voltage that could be possible. That we had discussed in the 2 weeks before discussion. So if you multiply this kW with L, that will be effective turns anyhow. Now see that this is at the stator induced EMF. Now if you look at the rotor EMF, so there will be slip concept coming in. So now at any value of slip, let's say at some value our rotor is rotating, there will be some slip related to it. Now, if I want to write the same equation for rotor EMF, now for any value of slip S, rotor EMF, I'm calling it as E2 subscript S, E2S, because there is slip associated with it. Can someone guess it? Root 2 times pi. Now the frequency won't be F. When you are having the slip concept here, the frequency of the rotor will be slip frequency, which is SF. That is the frequency of all the electrical quantities that present in the rotor circuit. Whatever might be the voltage and current, the frequency of those quantities will be SF. So that also we discussed last week. Root 2 times of pi multiplied by SF, and the flux, and Kw2 and N2. So see now the Kw2 and N2 will be the winding factor and the N2 will be the turns in the rotor side. So that's similar kind of analogy with respect to stator, but important thing is the SF, the frequency of the rotor will be slip frequency, that is S times F. Now if you take common S outside, the rest of the factor will looks like root 2 pi F phi Kw2 N2. Now just observe this factor and this particular expression. See, both are induced voltages per phase. Now the rotor side one in the bracket, if you look like, this is the kind of induced voltage per phase in the rotor at S is equals to 1, right? If you just, as you have taken S is equals to common, but at S equals to 1, this will be the rotor induced voltage per phase, because S is equals to 1 and as slip frequency will be S times F, that is F only. That is in rotor standstill condition, because S is equals to 1 means standstill condition. So at standstill condition, this bracket term is nothing but the induced voltage per phase at S is equals to 1 in the rotor. So I am writing it here. This thing is voltage induced per phase at S is equals to 1. Rotor voltage induced per phase at S equals to 1, that is standstill condition. Okay. Now with these two concepts, let's draw the equivalent circuit of induction machine. We will look at the per phase equivalent circuit first. Like let's say rotor is stationary, and then we will look at the first condition, like how the equivalent circuit can be formed if understanding these two concepts. So that's why we discussed these two, slip concept and also the voltage induced concept. Okay. Before looking at, I want to just write a small ratio here. See, now you have E1 and E2S, and also I would write this bracket term as S at E2. There is no subscript here because subscript S will have a slip term. So this E2 will be at S is equals to 1. That also we have seen. Now, what will be the ratio of E1 by E2? Here the S is equals to 1 case. Now, if you see that, divide these two, E1 and also this E bracket term. So, pi root 2 pi f, root 2 pi f, everything will get cancelled. And what will be left? KW1 N1 and KW2 N2, right? That will be left. KW1 N1 divided by KW2 N2. So I am calling it this ratio as a A. So can anyone tell me what this A is? It's nothing but effective turns ratio. N1 by N2 is the turns ratio, but KW1 multiplied by N1 will give you the effective turns ratio on the stator side, and KW1 2 by N2 will give the effective turns in the rotor side. So when you're taking the ratio, it will be effective turns ratio. So that's what I want to talk about before starting our equivalent circuit. So now let's draw the equivalent circuit of induction motor interface. So I'm assuming my rotor is stationary. When I say rotor is stationary, S will be 1, the standstill condition. So my rotor frequency, which should be SF, will be F. S is equals to 1. Now, and I have applied voltage to the stator. Now, so there will be voltage induced in the stator, and let's say the V1 is the per phase voltage I have applied in the stator. And now if you see my secondary rotor side, it's stationary and also having the same frequency. What you are observing now at S is equals to 1, we have energized the primary with say some fundamental frequency, let's say 50 hertz source, and my secondary is stationary. I have short circuited it, and my frequency at both primary and secondary are same. And if you take the E1 E2 ratio, I'm getting a turns ratio, and the frequency is same. So how is the circuit looking like now? I'm just writing it the points. Rotary stationary and energized primary is energized with 50 hertz source. See, primary means I'm saying this stator circuit, and secondary is shorted. There is no load. I just shorted the all the three phases of the rotor such that it is standstill condition. And frequency at primary and secondary is same since rotor is stationary now. Now, if you take the E1 and E2 ratio, will be effective turns ratio A. So now, what is the circuit looking like? This is primary. I have applied F 50 Hz source here, and let's say in this per phase E1 is being induced, and this is the rotor circuit, and now I'm short circuiting it, and here it will be E2 will be induced, and the frequency will be F because of S is equals to 1. And now if you see the circuit is just like a transformer. Why is circuit like a transformer? Can anyone tell me? Because what exactly transformer do? transformer changes the voltage from one level to another level without changing the frequency, right? So at S is equals to 1, this particular equivalent circuit will be just like transformer, because there will be uh, frequency will be there, which is same. The frequency is not changing, but the voltages, if you see E1 and E2, there has been a shift in the voltage levels according to the turns ratio. So this is just like a transformer. But what's different will be, there will be some stator resistances and leakage reactances in this, and there will be magnetizing inductance as well, which is much higher than the R1 and X1. And even if you neglect this R1 and X1, V1 will be equal to E1, of course, but there will be stator and resistance and leakage reactances. So that's what I'm just writing it here. Stator resistances and leakage reactance R2 comma X2, and there will be magnetizing inductance. You know the importance of magnetizing inductance, right? We'll be discussing about this in this session, which is Xn, which is much higher than R1 and X1. So the reason also we will discuss. Just to set up the flux in the core, we need to magnetize it, so it will take much amount of current. So that's magnetizing current, and yeah, and E1 will be there. Okay, so these all will be present in the equivalent circuit. Now, if you see the per phase voltage, how the circuit would look like. This will be R1, this will be the X1, and I have given a voltage here, and there will be Xn. If you remember the equivalent circuit of transformer, it will also have the same kind of Xm parallel branch with respect to R1 in series with X1. So similar kind of thing it will be there here as well, because it's just like a transformer. Now here it will be E1 induced, R1, and this will be X1. If you neglect this R1 X1, that V1 will be almost equal to E1, but usually there will be R1 and X1 existence in the stator side. Now see, this is the per phase, and this is per phase voltage it will look like. So if you see the total three phase, it will, I'm just showing the top portion, you can assume. So this particular V1, and this will be the E1, and here this part R1 and X1, whatever it is existing there. This will be in the primary side. Now if you see the secondary side, now secondary is what, at S is equals to 1, right? And induced voltage is E2, right? And now E2 is induced. It will also have its own resistance and reactances. I'm calling it as R2 and X2, and then it is short circuited. There is nothing there, and current will flow, and the frequency will be F here. If you see the three-phase circuit, and here it is E2, and frequency will be F. This particular thing is short circuit. This will be at the secondary side. Now we are seeing some notations here: R1, X1, R2, and X2. So these are nothing but the stator resistance per phase, stator leakage reactance per phase, rotor resistance per phase, and rotor leakage reactance per phase. So stator resistance per phase. Stator leakage reactance per phase, and it is rotor resistance per phase. Per phase. So here you have to which I wrote it because the important thing which you have to note it here is this x2 is when the standstill condition is happening. So then only it is x2, because if it's not in standstill there will be some slip existing, right? So reactance is usually depends on frequency, right? At s is equals to 1, since the both rotor frequency is equals to supply frequency, that's why x2. But when motor runs, your rotor frequency would change, FR would change. So this is x2 at standstill condition. Right. Now, let's say my rotor is having, yeah, now my motor is rotating now. S is not equal to 1 anymore, then FR is equals to SF, and my reactance is dependent on the frequency, because X is equals to omega L, right? Omega is equals to 2 pi F. So it's frequency dependent term. That's why when your motor runs, your FR will change. So the reactance value must be modified now. So that's how your reactance should be modified if there is if this condition exists. So X2 would be modified, that we will look into now later in subsequent discussions. So now that's for later part. Now we will see the first simple part, which is at standstill condition. We will arrive at the induction motor through this discussion, so that will be much more easy to understand. Okay, now back to our discussion. Now we have the primary side equivalent circuit and the secondary side equivalent circuit. Now we want to connect this primary and the secondary circuit using some standard circuit analysis concepts, right? The ultimate aim is to arrive at the complete equivalent circuit. That's today's discussion point. Now, at S is equals to 1, which is our present condition, your rotor frequency is equals to stator frequency, which is equals to F. Now, it is again just like a transformer. Now, equivalent circuit, I'm referring every thing to the stator part. At is equals to 1. So I'm just writing it. S is equals to 1, FR is equals to FS is equals to F, and E1 divided by E2 is equals to A. Now this, I'm trying to join equivalent circuit referred to stator, and again at S equals to 1 only, right? So yeah, this is the V1 I have applied here, and there is R1 X1. You see this particular equivalent circuit that is already referred to stator. That's already a stator equivalent circuit. Okay. Now this is XM. Now I am trying to join this particular thing to here. See, this is already at the same frequency, so I can easily add it. I just have to change these two terms with respect to the stator. So you know if it's a resistance or reactance. If you want to refer it to some other side, if you are referring a rotor quantity to stator quantity, you know the turns ratio. What will be the resistance? It will be multiplication of a square times. You know that, right? That is simply V1 by V2 is equals to I1 by I2. V1 by V2 is equals to N1 by N2 is equals to I2 by I1. So from there, if we calculate the resistances, it will be N1 square by N2 square. So that will be the A square term. So Z1 is equals to Z2 times of A square. So if you want to get the equivalent reactance or resistance referred to stator, you have to multiply with the square of the turns ratio. So I'm just writing it here. So this is x2 referred to stator. This is a square x2. So this is r1 x1 xn a square x2, and this is a square r2. That's okay. Now this is what we have arrived with. The equivalent circuit refer to the stator side when s is equals to 1. S is equals to 1 is a very simple case because frequencies remain same and there won't be any problem in joining these two circuits. Now the important question is, what will be question what will be the equivalent circuit when motor is running? That means S is not equals to 1, right? This is the important discussion, and that is what actual induction machine equivalent circuit we want to look at. Now the stator side remains same. There is nothing much difference you would see in the stator because there are R1, X1, XM, V1 you are giving, E1 will be induced, everything is same. And the rotor side, because of this running condition, your parameters and quantities are not same anymore. See, now see, since S exists, frequency at primary and secondary will be definitely different. The slip frequency would come because of those. What are the changes you would come? Because now the frequency is SF hertz, right? Frequency is 50. If it be 50 before, now it will be 50 times slip. So X2 will become SX2 frequency times the frequency is S times. If X2 is equals to 1, SX2 is at slip is equals to S. My frequency is SF. My voltage induced will be SA2. So these are all at the standstill condition or S is equals to 1 condition. So these are all at the running condition. Now S is not equal to 1 in this condition, right? Now if this condition exists, how will my secondary would look like? I would just draw the stator. There won't be any change in the stator. So it will be the xn. This is r1 and x1, and e1 is induced here. And now if you look at the secondary side, there will be some induced. Now this will be s times e2 with this here, and my frequency is sf, and my resistance will be R2. Resistance is independent of frequency, okay, that won't change, but your reactance will be S times of X2. Now we can't just connect these two here because primary and secondary are not at the same this same frequency, and if you see the E1 by E2, which is SE2 now, this is not is equals to A anymore because a slip is coming into picture here. Now you just can't simply connect primary and secondary just by multiplying with A square terms ratio. That's not going to happen. Now how to overcome this situation? That's a key point here. See, let's say your motor is operating with slip S, and if you see the secondary circuit, there will be some current, right? I2, if I call this as I2, that I2 will be at slip frequency SF. Now what will be the RMS value of this rotor current I2? We are slowly moving towards the key understanding of how we can join these two. So the first step we will be taking is to calculate the current. So let's see what the current that is flowing in the secondary side. Now using just uh, using this KVL, just you can tell me the value of I2 here. So I2 is nothing but the voltage divided by the entire impedance. So voltage is as E2 here divided by the impedance. Impedance is R2 plus JSX2. Right. So that is if we take the resultant R2 square plus SX2 square. So this is the RMS value of rotor current. Right. Now this current I2 is at frequency SF. At SF frequency, this is the SE2 by root of R2 square plus SX2 square. Okay. Now I am just modifying this term into this part. I'm just rearranging it. I'm just dividing the entire expression by S. So if I divide numerator and denominator by S, the numerator will become E2 and I will divide by S also here. I will take it inside and R2 by S whole square plus X2 square. Right? Now if you see this expression and this expression is same, I just divided by it S. Now if you see these terms here, E2, R2 by S and X2, this also represents some kind of circuit, right? If I want to draw that kind of circuit, so see this SE2 is this voltage, R2 is the resistance and SX2 is the reactance. Now if I just apply same to this one, I try to draw some circuit here. This will be E2 and there will be a resistance and the reactance. From the expression, that is what I understood. But the resistance value is not R2 here, R2 by S, and the reactance value is X2, right? But the current flowing is I2 only, because I2 expression is same, but the circuit is something I have rearranged it into so that I can get a different circuit. Let's say this is rotor circuit A and this is some circuit B. In circuit A and circuit B, the magnitude of I2 is same. It's just rearranged and we got two different circuits. Right? Now, let's discuss a very interesting concept, that is, let's say we have a transformer. I open circuit at the secondary side. I will come back to that point because to understand that we need to understand this point. Secondary is open circuited. Now my secondary is not drawing any load, not driving any load. Now whatever current my primary is drawing from the supply is only the magnetizing current. That's the principle of transformer. So it will draw some magnetizing current because there is no secondary circuit. Nothing is there connected. Open circuit condition. So this is the primary and this is the secondary, and I have open circuited it and I have supplied some V1 and there is no circuit in the secondary. So whatever current it will draw, that will only be to magnetize the core. Current, right? But let's say I'm trying to draw some current in the secondary side. So what I will do, I will I will just connect some load, and the moment I connect some load to the secondary, it will definitely draw some current because to drive that load, you have to draw some current. The secondary will definitely draw to some current. So, but in the primary, don't forget about the secondary, whether it's open circuit or closed circuited, the flux in the core should always remain same. So that's the basic principle. The flux remains same in the core. Now, let's say in this, I have connected a load via a switch, This is the switch, and I tried to close the switch. So the moment I try to close the switch, my secondary will draw some current, right? Some current will flow because there is a load connected here. So no matter what we do in the secondary or closed open in circuit, the flux in the core is always fixed. That we know. So there is no change in the primary. I am not changing any circuit in the primary because KVL is satisfying here. So flux is being decided by the applied voltage because there is no change in V1 here. V1 is fixed. So the E1 will be fixed. So the current drawn to magnetize the core will be fixed. But I have connected a secondary now. It should draw some current. So from where this current will come? So how it will manage to generate that current? Any idea? Because my magnetizing current will always be same because I have set up the core. I have set up the core. Now it is being magnetized. It won't draw more any more magnetizing current because the flux should in the core will always be fixed. There is no change in this primary I did. V1 is fixed, E1 is fixed. Now, the moment I connect the load, the I2 will be drawn. From where will the current will be coming? So here, the important concept will come, which is the MMF balance. MMF should always be balanced in a transformer in both primary side and the secondary side. The MMF should be balanced. So if you understand the MMF barrel concept, so then you can understand it how it managed to do that, how it managed to draw that particular amount of current I2. Because under no load, let me just write the word here. MMF is what? Is nothing but ampere turns, that is turns multiplied by current. So N1 I1 is equals to N2 I2. So this should be followed always. Now see, if you see in the first case, under no load, that means load is not there, open circuited. Primary is drawing only magnetizing current to what is the purpose of drawing it? To establish the flux in the core, right? So it's done now. In the second case, we have connected a switch and tried to connect a load to the second. So the moment we close the switch, what will happen? I2 will be passing, secondary current will pass, right? Secondary current will pass. Therefore, some extra MMF is being generated. There is a I2 current, new current is there, extra current is there. I2 multiplied by N2 will be extra MMF, which is now newly brought into the system because load must be balanced. The load connected must be balanced. So I'll write that also. Secondary current will pass, extra MMF is brought into system. So my primary, what will my primary should do to do MMF balance? So then my primary must draw some additional current along with this magnetizing current. Because see, I will write it here. So now the another thing that will happen is my primary must draw. That's the compulsory condition. So that my primary must draw some additional current. Why it is drawing the additional current? See, this additional current is along with the magnetizing current. Just to have a MMF balance. So this additional current we are calling it as the reflected current. So this is important thing which you have to understand it. So IM is being drawn by the primary because of the magnetizing current. That's okay. So when under no load, IM is the primary current and secondary current is zero. There is no load here. So this is, I'm saying it, the open circuit condition. Now there is a load connected. Now if you see in the loaded condition, first I know for sure secondary is drawing some I2 current. So IM is anyhow fixed because my flux in the core is fixed. I know how much magnetizing current is required to set up the flux. Now, because of this current I2, my stator will draw some reflected current which is similar to this I2, but it is I2 dash, that is something in terms of stator. So this I2 dash, it will be drawn by my primary here in the loaded condition. Now this value of I2 dash will be such that my N1 I2 dash will be equals to N2 I2 dash. That's the important concept of MMF balance I am talking about. So here N1 I2 dash will be equal to N2 I2. So the value of I2 will be such that this equation will be satisfied. I2 dash will be satisfied. So that says that there will be a MMF balance will be there. Now these two MMF will be equal and opposite because this amount of MMF produced in the secondary that is being counterbalanced by the MMF in the primary. There will be a balance. If this is positive, that MMF, there will be negative MMF. Positive, negative means in the amount of direction. So these two MMF will cancel out each other, and again, therefore, the flux in the core also remains same. Only that is due to the N1 into IM. That is the magnetizing current. So that's the concept. So whatever might be the load current that will be drawing by the rotor, same amount of reflected current will be drawn by the stator to provide this MMF balance, and the magnetizing current MMF should always be remains the same. So now that is what the important concept. So after all this discussion, two important points I want to note down. First one is, if you have unloaded secondary, that is secondary of your transformer is open circuited, the current drawn by the transformer is only magnetizing current. If you have a unloaded secondary, that is secondary of the transformer is open circuited, then the current drawn by the transformer primary is only magnetizing current. Okay, that's clear. And the second important point is, if we close secondary with some impedance, some load to draw some secondary current, if you connect a load to secondary to draw some current, that is in secondary, primary would not just look at this and do nothing about it, but it will also immediately react. Primary will react by drawing extra current, which is I2 dash, such that what will happen? Such that MMF balance will be occurring. So this N1 I2 dash is equals to N2 I2. So they both cancel out each other and total MMF existing in circuit is once again N1 IM. So these will both will cancel out. Therefore again total MMF existing in the circuit is once again N1 IM. So the flux remains constant. Why did you say once again here? Because in the first case also only magnetizing current. Here also the flux is MMF is N1 IM. But in secondary condition, even when the secondary is loaded, here also my total flux will be MMF magnetizing flux only. That is N1 IM because my flux should remain constant. So now we will take this concept. So see, why did we start this discussion? Where we are trying to join the primary and secondary, right? So we started this discussion because in this condition. So till this point we have discussed, we got two different circuits which are having same current I2, and then we discussed this concept of MMF balance, and now we will see. See, now let's get back to our three-phase induction motor machine equivalent circuit. Now I energized my primary with some three-phase voltage. So primary is energized with three-phase voltage. Now what will happen as soon as I energize with the three-phase voltage? That we have seen in the last week discussion. RMF, how the RMF is being produced, right? So as soon as I do it, RMF will be produced and voltage will be induced, and of course there exists flux per pole. Now if you neglect R1 and X1, this amount of induced voltage will be almost equal to the how much we have energized the winding with. So V1 will be equal to E1. So I'm writing it here. If you neglect R1 and X1, just to getting the formula of it. So this formula we already discussed, root 2 times pi f phi, this is flux per pole, Kw1 N1. That is we know. So now if you see the formula of flux from here, flux is equals to V1 divided by root 2 times of pi frequency Kw1 N1. Now whether the secondary is open circuited or connected to something or anything happens on secondary, this flux per pole should always remains constant. So that's what we have seen now. So this flux is required to magnetize the core, and whatever happens on the secondary, this flux per pole should remain constant. Okay. Even last week, before last week, we saw the discussion of flux per pole derivation where we have 4 by P times some discussion like this. 4 by P B net length into diameter. I think it's 2 by P diameter and it's 2 times radius. That is the area of cross section of the pole we saw. So here, the flux is always dependent on this net magnetic field density. See now this B, which is having unit of Weber per meter square, and that is in turn dependent with the flux per pole. So this strength of this B should always remain same from no load to full load. So that's what I'm writing it here. So whether secondary is open circuited or loaded condition, the flux per pole should remain constant. And now flux is of course dependent on this strength of B. What I meant to say is the strength of B remains same from no load to full load. No load to full load means what? Secondary is no load to full load means you are changing secondary for different loaded conditions. You are starting from open circuit and you are going to full load condition. So whatever might be the loading condition of the secondary, the strength of B should always remain same. Okay, that's what I meant. So this is now, let's say this is primary. So I have energized with a three-phase voltage here, three-phase voltage, and that's I have energized with RMF is produced, and then voltage induced. Everything is happening. Now there is secondary here. Instead of short circuiting it, now I have connected a load here. So I have closed the switch in the secondary side. So there is uh, some loaded condition. So each phase I have connected some load and I have closed the switch. And this secondary side, what will happen? This MMF, it will draw some current, and this particular MMF needs to be taken care by primary. So switch closed, secondary current will pass. As a reaction of it, my primary will draw this I2 dash just like the transformer, so that the MMF is taken care of. See the magnitude of B net here, that's the concept, right? The magnitude of this B net should be, it remains same. The flux per pole should remain same, so that magnitude of B net as well as flux per pole remains same. So that's the concept. Now let's get back to our original discussion where I have two currents, right? I have connected I2, that is SE2 at R2 square plus SX2 square. So this is actual condition we have taken when the machine is running and your slip is not at 1 anymore. It's not at standstill anymore. You have some, and this is the stator, you have energized it, and RMF is produced, and the stator field is rotating at the speed of ns. We have discussed this, right? The stator field and rotor field will have ns speed, where the rotor speed will be nr. Now I have this rotor here, I have some load here, so that it will draw the current I2. Now this is rotor and this is stator, and see here my rotor is rotating with nr speed. See now, what I will do is, with respect to the stationary observer, so let's say observer is sitting on the stator, he is stationary, the stator is stationary. If he observes the speed of rotor field, what is it? We discussed this. Not speed of rotor, speed of rotor field is nothing but ms. Speed of rotor field with respect to stationary observer is ms. So he is seeing, he is not moving. Observer is stationary. He is just sitting on the stator and he is seeing the rotor field. So the stator field is ns, rotor field is ns, the rotor speed is nr. So he is stationary. So he will see the rotor field as ns. Now this is the actual motor which is running condition. So I am naming this machine as machine A, that is this actual motor in the running condition. See now let's get into another kind of discussion. Now we know for a running motor this is how the I2 would be. Now I would ask you to imagine an induction motor which is stationary. Okay, stationary means what? Your rotor is locked. So this is the actual motor case. So I am trying to get to a machine B. This is imaginary machine. This is not the actual motor, but I want you to imagine imaginary induction motor, which is a stationary condition. See, only a rotor is locked. My stator remains same. Okay. For this motor, stator is same, rotor is also same, except that the rotor I have locked it. Now while designing it, I will design the rotor as stator as same. Rotor will also be the same, except that I will design the resistance of the rotor. Here it is C, here it is R2, right? Except in this condition, in my imaginary motor which is a standstill condition, my rotor resistance I will design it for R2 by S. See the same S here. See, when I said it's a stationary condition, you know its slip is equals to 1. So don't confuse that where this slip has come. So this slip is not of the imaginary motor. So from this actual motor, I will calculate the slip. See this, I know the value of slip here, right? S. So I know the slip of actual motor. So while imagining my imaginary motor, I will design my rotor resistance such that my rotor resistance is R2 divided by S, where this S is slip of actual motor. So this is important. So I will manually calculate the S and I will manually make my rotor resistance as the R2 by S. So if you see the equivalent circuit for this, like this particular diagram, my stator is same. Okay, stator is same. And now if you look at the rotor side, my rotor is locked. I have short circuited it. If my rotor is locked condition, what will be the my reactance? S is equals to 1, right? So reactance is x2. My resistance is anyhow it should be R2. But what I did, my R2 I designed it as a R2 by S, where S is equals to slip of the actual motor. Now what will be the induced voltage? It will be E2 because S is equals to 1 here, right? SE2 it actually should be, but S is equals to 1 since my imaginary motor is at stationary condition, it will be E2. E2, R2 by S and X2. Now what will be the frequency here in the rotor frequency? Since S is equals to 1, my rotor frequency will equal to same as the supply frequency. Now if I draw the secondary side circuit, so there will be a voltage induced, right? There will be a resistance and there will be a reactance. So this is E2 and this is X2 and this is R2 by S and the frequency is F. So see, so this is R2 by S. If you see this, R2 by S is a fixed number. So we choose that particular R2 by S for this particular standstill motor because standstill is FR is equals to F. Now, in the top case, you know the I2 current, SE2 by root of R2 square plus SX2. Now, if you calculate the current in this condition, so what will be the current? I2 is equals to RMS value. So the voltage is E2 divided by my resistance is R2 by S square. My reactance is X2 square. See, the both currents are same, and I2 here is flowing at a frequency of F because slip in this condition is 1 and FR is equals to F, so I2 condition will be same. Now, here comes the interesting point. Now, some observer is sitting on the stator of these two machines. So, one is actual machine A and one is imaginary machine B. So, this actual running machine, imaginary standstill machine. So this is the stator. Here observer is here and this is the rotor of it. Rotor of actual machine. So it will be SE2, frequency is SF and this is the loaded condition, running machine. Now here it is the stator of imaginary motor, everything is same. Here again observer is sitting, but here in this case my rotor is standstill, right? I have short circuited it and E2 frequency is F and the current flowing is I2 here in the actual motor and here frequency is F but the current will be again same I2. That's an interesting case. So because of this current I2, your RMF will be generated and there will be rotor field will be coming up. So the stator will have NS here, stator will have NS speed, stator field will have, and here rotor speed is NR and the rotor field speed is NS. Rotor field, NR is the rotor speed. With respect to this stationary I am talking. So here again rotor speed is 0, it's in standstill condition. But the rotor field will be NS only because same current is flowing in both. Now the stationary interesting thing is you are sitting on the stator of these two machines. If I ask you which machine is rotating and which machine is standstill, you cannot say it. Because according to you, you are sitting on the stationary stator and for the both rotating machine and also standstill machine, the fields of the rotor are same. That is NS, both are having the NS rotor field. But even though your rotating machine has R2, here it is R2 and SX2. Here it is R2 by S and X2. Even these parameters are same, induced voltage is different, but the same current is flowing, and therefore rotor field that is produced by both machines are equal strength, and both fields will rotate with the same speed of ns. That is the important concept here. Why we have imagined this, that will I will tell you, because we are just arriving at the actual equivalent circuit of induction motor. So the main point is the stationary observer cannot distinguish the rotor fields between these two, because both will have the same speed, because the same rotor current is flowing through with these both machines, and the rotor field produced by these both machines will also be of equal strength. So why did we start this discussion? So the main discussion question came how we can directly connect the primary and secondary if we have a slip in picture. That's the question we have come up with. So we are kind of solving that question by taking an imaginary motor with a resistance of R2 by S and a standstill condition. Now in these both cases, I2 is remained same, power factor is remained same. See, if you see the power factor in this case, power factor of machine A will be what, tan inverse of Sx2 by R2 in this case. We will take cos of that, of course. Power factor angle I am taking here. Here the power factor angle will be tan inverse of x2 by R2 by S. So these both are same. Now the power factor is same, I2 current is same. Therefore, the stator will react in the same way in both cases, because stator has to draw some current I2 dash. So in both cases, stator will react in the same way while drawing this I2 dash. Therefore, what people have come up with the solution to overcome this problem of joining these two circuits, primary and secondary, when slip is in the picture, is they have modified the secondary side of the circuit to bring the frequency to the same as input frequency, but the mmf should remain same, but the rotor field should remain same, and the amount of current drawn should remain same. See, because we are keeping the current I2 same in these two cases, but we are kind of modifying this frequency. See, here it is slip frequency, here it is same as input frequency. Here it is kind of SE2, but here it is kind of E2. Now, if we go back to the discussion here, where in this condition, see, here E2, R2 by S and X2, it is easy to join. But here it is SE2, SF and these are not different. So you can't combine these two here. But now what people have come up with the solution, they have modified this secondary rotor circuit to a pretending that in a motor to be a stationary motor at standstill condition with a different kind of resistance. So that we will see now even more clearer. Let me just get more slides. So it's nothing confusing here. We are just kind of modifying the secondary by pretending it as a standstill motor with a different parameters changed. See, this is the stator circuit, and I'm drawing the final. I'm coming to the final equivalent circuit, but step by step, of course, we will go. This is the stator side. This is R1 and X1, and this is JXN, and this is V1 we have given here, and this here there is E1 being induced. Now, if you see our original secondary, we have a actual motor, that is SE2, having a reactance of SX2 and a resistance of R2, having a frequency of SF, drawing a current of I2. That is what we are actual. This is the actual motor. Now the solution people have come up with is they are changing this secondary circuit to SE2. They are changing it as a E2, and the this reactance will be X2, and the resistance will be R2 by S, and the frequency is F, and the current is still R2. So this is not the actual motor. They are pretending it as a stationary motor, standstill condition. See, in these both cases, stator can't differentiate which is which machine, because in both cases I2 is same. So the amount of current my stator should draw, that is a reflected current, to maintain the MMF balance will be same in both cases. So there is no difference. Your behavior in the stator won't change. That's what. That's how they have changed the circuit so that it will be easy to join both these equivalent circuits. Now see, in the secondary and the primary, you have the same equivalent circuit. So now E2 will be there, same frequency. You can just join these two by multiplying the turns ratio. Because if you again E1 and E2 are here, it's not slip is not anymore a problem here, and also the frequencies are same. Now if I join these two, now the equivalent circuits can be combined. R1, this is the stator side I am joining. This is V1, R1, and X1, JXN. And now I'm joining these two. This X2 will become A square X2, and this R2 by S will become A square R2 by S. So see, this is the X2, which is standstill leakage reactance, because this is the equivalent circuit, X2, which we have assumed to be a standstill condition of the machine, right? Now I could have we could have just skipped this entire discussion by just taking that, okay, it's just nothing. You divide all the expressions by divided by S here, and it will be E2 X2 and R2 by S, and you can join it. But that's not how we should understand the equivalent circuit concept. Why do we have to divide it? What happens when we divide it? Will that division makes any change in the behavior? So why are we dividing it? So every discussion, whatever we discussed for the past 1.5 hours, is very important. The reason we are changing it because to pretend that, like, to bring a situation where the input frequency and the rotor side circuit frequency are same, so that I can join these two by keeping the behavior of the machine same. My stator should not find any difference between these two circuits now. So that's why we discussed this, and how my particular stator is seeing the circuits. Excuse me, Sham. Yeah, thank you. So now we have joined it. Now the problem is solved. We got the equivalent circuit of the induction machine. So this is nothing but the equivalent circuit of induction machine refer to stator. See, this is of course three-phase induction motor. Per phase equivalent circuit we have seen. So we know this R1 X1 R2 X2 are much smaller than the magnetizing reactances. Now one important concern which we are forgetting about the circuit, we have changed everything. So will that not change anything else? Everything remains same. So there is one concern in both the circuits which I'm having a problem is these both are identical in every respect. See, I2 is same. I'm just writing it. Yeah. For circuits A and B, I2 is same. My power factor angle is same. My flux is same. Rotor field speed is same. But there is a massive difference in one quantity because you are experiencing a difference in the resistance. So that difference in the quantity will be active power. See, now in the case A, for the active power of case A will be per phase if you see I2 square R2, right? Now for the case B, that is imaginary motor, what is the active power in the second case? This is I2 square multiplied by R2 by S. See, this R2 by S is much bigger than the value of R2 because slip is in like 0.04, zero 0.5 or something in that range. Now, if you be dividing it by R2, it will be much higher. Now, my active power in case of your fictitious motor, that is imaginary motor, now PB will be much greater than PA, that is deviating from your actual motor condition. So, how can someone explain this? Because in your actual machine you are having only less amount of active power, right? So what happens in this fictitious power, why you are getting so much? This everything is balanced, right? mmf is balanced, current is balanced, power factor angle is balanced, flux is balanced, but active power is not balanced. How can someone explain this? So even this is explainable, even this is also balanced. So this can be explained in the case where you are forgetting about the mechanical power that is being utilized. Now the only difference which we have seen is the active power, and the another difference is the actual motor is running condition, but your fictitious motor is standstill condition. Now in the actual case when the machine is running, there will be some opposing torque, right? So whatever it is you are moving, you are observing, there will be a opposing torque. So that's where this power is being compensated there. So then in actual case, machine is running. So there will be opposing torque exists. So friction or some load torque, everything will be there. Friction torque, load torque, all these kind of conditions, torque, opposing torque conditions will exist in the actual motor. Therefore, there is locally I square R losses will be there on the shaft, right? But on shaft, motor power is being dissipated there, right? Which is in terms of mechanical power. So these two powers together should be supplied by this our machine, and this must be drawn by the primary only. So whatever side, whatever power you are having on the secondary side, this mechanical power and also this copper losses, everything should be supplied by primary only. In your actual motor case, you have copper losses and also mechanical power losses. There will be local copper losses, which is I square R losses, and also mechanical power losses will be there. Now, these both will be contributed by the primary in the actual machine. Now, while coming to the imaginary motor, your motor is at standstill. So we already discussed that in stage the stator can't distinguish any machine. So even in this case, active power drawn by the primary must be same. So hence this R2 by S, the factor that takes into account of both copper losses and also mechanical power which is in the actual machine. So see in this actual actual machine, your R2 is there. That is some copper losses it will take care. And apart from this, there are also mechanical losses. That is this friction, this opposing torques, everything will be there. And now in this imaginary motor, only copper losses will be there, but the resistance is R2 by S. So if there will be much higher copper losses, here it will be copper losses and mechanical losses. So these two losses will be taken care by this R2 by S term. So the exact same amount of losses you can observe. That's the beauty of this concept. So everything, everywhere, all are being balanced by this particular imaginary motor. So if you see now, if you want to see, if you want to get this mechanical losses, you have to just subtract this actual copper losses from the fictitious motor copper losses. So, see, this is the fictitious motor copper losses. That is, if you take the copper losses of the total machine, I2 square R2 by S. Now here the copper losses are I2 square R2. So if you subtract this actual motor R2, so this is the copper losses of imaginary motor. This is the copper losses of actual motor. If you subtract this from this copper loss of imaginary motor, then you will get the mechanical losses, mechanical power. So if you remember, this is a very important relation in induction machines. This is how we got the relation. P mechanical power is nothing but the 3 I2 square R2 by S minus 3 I2 square R2. So again our fact is satisfied here. So whatever it is, the active power is being balanced out in the imaginary power by compensating for both mechanical and copper within this I2 square R2 by S copper losses. So see, we are already 7:30. We have only half an hour to solve the problems. So in the next week, we will discuss the entire power flow diagram of the induction machine. Even further, if we see, we will see the equivalent circuit and Thevenin's equivalent of it, and some interesting derivations we will see, and also the concepts of inserting the external resistance in the circuit, how the torque speed capsule will say. I would say the next week discussion will be continuation of it, and it will be even more interesting. So today we have discussed the arriving of the equivalent circuit of a induction machine when during the running condition or standstill anywhere, whatever it is, we got the equivalent circuit and the underlying principles of it. Now with this, let's solve the questions. I would request everyone to take pen and paper. It will be very simple. If you understand the discussion for the past 1.5 hours, it will be very easy. So yeah, let's quickly solve the questions with me. So everyone take a pen, paper, and also calculator with you. We will solve these questions. So we were given with the problem to consider a three-phase, six-pole, 50 hertz induction motor. See, the rotor is star connected with per phase standstill resistance is given and also reactance is given. So the information which they are giving is a standstill. Okay. Now, when the stator is excited with the rated supply, the induced EMF in the rotor is 120 volts per phase at standstill condition. Okay. Estimate the rotor current at the starting. See, all the information was given. We just have to substitute and get the answer. It's as simple as it is if you understand the discussion now. So, every detail in the question is important. They gave us standstill reactance and they're asking us to calculate the rotor current at the starting. So just note down whatever it is given for us. Now, rotor current at the starting we need, right? So what is the formula you know for I2? It is SE2 divided by R2 square plus SX2 square. So this is the formula for rotor current at any slip condition, right? This is what we derived today. Now they gave that rotor current is at the starting. So this the equivalent circuit will be SE2 and it is the R2 and SE2, R2 and SX2. So secondary circuit we are looking at because rotor current they are asking. Now at starting condition, S is equals to 1. Starting means NR is equals to 0. And S is equals to 1, we are also calling that condition as standstill condition. Now at that standstill condition, we are already given that E2 is equals to 120 volt per phase at standstill. And at standstill condition, that is equals to 1, R2 and X2 are also given. So standstill resistance and standstill reactance. So it's just I2 we have to calculate. It is 120 divided by 0.25 square plus S is equals to 1, X2 is 1 square. So we calculate it 120 divided by 25 by 100 square, 1 by 4, 1 by 16 plus 1. So it will be around, you verify it, 116.417 amps. So this is the rotor current at the starting condition at this given standstill values. So we did nothing. We just know the formula of our rotor current at any slip condition. We have just substituted the values. Now the second question, estimate the rotor power factor at the starting. So power factor is cos phi and phi is nothing but the angle between it. Now we already calculated this. Now see, cos phi is, we know, R by Z, the resistance by impedance from the impedance triangle. If you see, cos phi is the R by Z. Now R is the resistance, Z is the total impedance. Now R we know, and R2, of course it is at the starting condition they have asked. So R2 at the starting is called the standstill reactance. Now Z will be total impedance. Now R2 square plus S X2 square, S will be 1 because of the starting. Now cos phi is equals to R2 is 0.25 standstill resistance under root 0.25 square plus standstill reactance 1 square. So if you see, it is 0.2425. So if you see, at starting condition, your rotor is having a very poor power factor, 0.24. Usually to improve this power factor at the starting, what will people do? There are some good starting methods and also external resistance they will add to the rotor at the starting so that it will be improved. That we will discuss in the uh, next week clearly. But I'm just giving a introduction of the discussion how people can improve the standard starting power factor. Okay, this is simple substitution again. Okay, now torque discussion we have not discussed this week. If time permits, I would discuss the torque derivation in the today itself, or else we will discuss in detail the in the next session. Of course, we discussed the power, that is uh, mechanical power, and to discuss this torque, we need to discuss the air gap power and also mechanical power, etc. But I would say we will just discuss the direct formulas here. I will discuss complete thing in the next week. Even more detailed derivations we will see. So see, now torque at the starting it was asked. So this electromagnetic torque formula will be air gap power divided by 2 pi ns. We will see the detailed discussion. This air gap power, when we discuss the rotor power flow diagram, it will be even more clearer. So there are some equations which we need to understand. One we have seen, that is P mechanical is equals to 3I2 square R2 by S minus that one. See, let's write it here only. That's important one. See this P mechanical and 3I2 square R2 by S, 3I2 square R2. See this 3I2 square R2 is nothing but the rotor copper losses, right? And 3I2 square R2 divided by S. So if you see this P mechanical is equals to uh, P I would say one more thing is air gap power is there. That is rotor copper loss is slip times the air gap power. That is I'm writing it here. P rotor copper loss. Don't worry, this derivation we will see clearly in the next week. This is slip times the air gap power. So 1 minus S times the air gap power will give you the P gross mechanical power. So these two equations are important. Next week we will see in this condition. So now if you see at standstill conditions, the problem is given. Torque at the starting we need. So S into air gap power is equals to P rotor copper loss, and 1 minus times of air gap power is equals to P gross mechanical. Now since S is equals to 1 here at the starting, now P gross mechanical will be what? S equals to 1, if you substitute here it will be 0. So air gap power, if S equals to 1 substitute here, air gap power is nothing but the rotor copper losses. So if you see this formula, air gap power is nothing but the rotor copper losses now. At the starting condition, there are no mechanical losses. So you will just have to calculate the rotor copper losses and divide it by 2 pi ns to get the torque at the starting. So how to calculate this rotor copper losses? That we know. That is 3 I2 square R2. Now I2 we have calculated in the previous problem. 116.4 square multiplied by R2 at the standstill, because at the starting condition 0.25. Now if you multiply you will get around 10.16 kilowatt. Now we have just to divide it by 2 pi ns. Before that we will just see what is ns. Ns, you know the formula, mechanical RPS 2F by P. What is the supply frequency? It's given in the problem 50 hertz, and this is a 6 pole machine. So what is its 50 by 3? Ns is 50 by 3. Now the torque will be at the starting power, that is 10.16 into 10 cube divided by 2 pi into 50 by 3. So you can calculate it, and you can get the starting torque. That is, you calculate it, if you starting torque you will get around 97.03 units of torque is Newton meter. Yeah, so this is how you will calculate the torque. After next week in discussion, you will even more understanding how the formulas have been got. But for now, you have to, you already know power. If you know the power, you have to just divide it by speed to get the uh, torque. Okay. Now the next question: find the rotor current at the speed of 960. So now our rotor is not at standstill anymore. There exists some speed of the rotor. So then there exists some speed of the slip of the motor. See, now we have given RPM. RPM means NR, right? Capital NR. Capital NR is given 960. So let's calculate the slip now. So what is the slip formula? NS minus NR by NS. So what is the NS? 120 F by P. So 120 F by P, we were provided with the 120 supply frequency and also poles of machine. 120 into 50 by 6 pole. So it's a 1000 RPM. So now to calculate the rotor current, we know the formula. S is equals to, let's calculate the slip first. 1000 minus 960 divided by 1000. So it's 40 divided by this one. This is equal to 0.04 slip. It's 4% slip. Now the rotor current formula which we already derived today, that is at any slip, because now the slip exists. SE2 divided by R2 square plus SX2 square. Now it's just again simply substituting that. 0.04 120 multiplied by R2. R2 is 0.25 square. Now it's not standstill reactance anymore. It's slip multiplied by standstill. So S 0.04 multiplied by 1 square. So anyhow, at standstill or any running slip, the resistance won't change. So it's independent of any frequency. Now this 0.04 into 120 divided by 0.25 square plus this we have calculated before. It's 0.04 120. You can also calculate using your calculator. It will come around 18.95 amps. So this is the rotor current when it is rotating at the speed of 960 rpm. Now, same thing. We are just asking to calculate the rotor power factor at a speed of 960 rpm. So, power factor formula which we saw in the before question is R2 divided by R2 square plus XS2 square. This is R by Z if you remember. Okay. Now, there is some slip. So, R2 is 0.25 divided by 0.25 square plus 0.04 multiplied by 1 square. So you will get a slip of 0.98. Sorry, you get a power factor of 0.987. See how the power factor has been improved during the running condition. So starting power factor will always be very less for an induction motor. So running power factor will be high. So that's why there are techniques where they will try to improve the starting power factor of the induction motor by adding some external resistance. That is one of the technique how we can improve the starting power factor. See, in the second question, we have calculated the starting power factor around 0.24 something we have got. That's very poor power factor. So to improve the starting power factor, people usually add some external resistance to the circuit. So the total resistance will be R2 plus R external. So that will give us a 0.997. Okay, calculated anything. But this is what formula 0.25 by 0.25 square plus 0.04 square. Okay. Now let's look at the next question. Find the torque. Same thing again. You have a torque now. Torque is but air gap power. Torque is equals to air gap power by 2 pi ns, and 2 pi ns will be 2 pi times of 2f by p. So first calculate 2 pi ns. Ns is in mechanical RPS, multiplying with 2 pi to make it as radians per second. Now 2 pi 2 into 50 by 6, and it is 4 pi 50 by 6. This is 2 pi ns, and now we have to calculate the air gap power. Air gap power, now there exists some slip. So slip times air gap power is the rotor copper loss. So if you calculate the rotor copper loss and divide it by the slip, then you can get the air gap power. So what is the rotor copper loss? 3I2 square R2 divided by S. I2 we calculated rotor current at this speed 960. This is the previous problem. 18.95 square multiplied by R2.25 divided by slip. This is 0.04. So your air gap power will come out to be some 6.73 kilowatts. Now you divide this with the 2 pi ns to get the torque at that particular speed. PAG divided by 2 pi ns, 6.73 into 10 cube divided by 4 pi into 50 by 6. So please calculate this. This will give you the torque of the rotor, like torque of the machine at that particular speed. So this will,
Yes, sir.
yeah,
So this air gap power we should like 1 minus s into PAG. That's the mechanical power.
yeah,
And speed we should take 960
yes,
without
960.
that 1000 RPM.
No, no, divided by 2 pi ns. That is stator speed only.
Yeah, but like torque now it is running, na? So torque will be the NR. You have to take the NR speed.
No, this formula came from, like, if you take the if it's not the air gap power, if you take the power of rotor, see, uh, while the derivation it will come, the 2 pi ns came from, it is what you call this, stay synchronous speed only. This air gap power, if you see the look at the derivation of torque, there will be a big derivation where you are converting this PAG by 2 pi ns. No, no, PAG by 2 pi ns. If it is air gap power, it should be rotor speed.
It is when the rotor is not rotating.
Rotating, yeah.
But now it is rotating at 960 rpm.
Now the air gap power, if you take it, it will be,
No, I will minus the copper loss. There is a mechanical power I will get.
yeah,
But
mechanical.
friction and windage loss has not been given.
But when the rotor is at standstill, there are no mechanical power loss, and
So it is
it will
a
be,
PAG while
yeah, yeah, yeah. If
now
it
it is
is
rotating
running, it will, air gap power will become air gap power, but
1 minus S into PG,
yeah, yeah, yeah. Then it will become NR.
mechanical power.
NR. 1 minus S into what it will be, in the previous slide I have written it right. 1 minus H will be PG, will be a mechanical power, right? Um,
And friction and windage is not given. Otherwise, we can calculate soft torque.
yeah,
But torque means it will be like 1 minus PAG divided by W 2 pi NR.
P mechanical. See this, mechanical torque by 2 pi NR, because that's a mechanical power. Now mechanical power is nothing but P minus S into PAG by 2 pi NR. Now NR is equals to NS into 1 minus S. Now see, now if you see, if I substitute NR is equals to NS
No,
into,
it is same, sir, I think.
yeah, that's what, 1 minus S, 1 minus S get cancelled. Now when it comes to air gap power, it will be NS only. Now when you are talking about mechanical power, P mechanical, that will be rotor speed. Now if I replace this mechanical power by 1 minus S into air gap, now 1 minus S by NR will be NS. You are taking the term out. That's how it is, PAG by 2 pi NS.
If they give friction windage and
Yeah.
they are soft torque, then it's a different.
If there is friction and windage also, so you have to calculate the mechanical power.
Okay, okay, sir. It will be the same answer, I think.
Yeah. No, if you if you take P mechanical by 2 pi NR and P air gap power by 2 pi NS, it will be same. That's
Yes,
what I want to
yes, yes.
tell. Okay. So now we are calculating the torque at the speed of 960 rpm. So if you substitute it, you will get around 64.2 Newton meter. Okay. Now these last questions will be interesting because they are asking the same induction motor. That's what I was also saying. Now they are adding an external resistance of 1 ohm per phase that is added to the rotor. Now we will see a interesting results also. See, now they're adding R R2 is now R2 plus R external. So they are adding 1 ohm to the existing R2. So everything remains same. It's just we will have to see how the rotor current is changing. So I won't be spending much time. After adding external resistance will be SE2 divided by R2 is now R2 plus external square plus S x2 square. Now slip at starting, so S is equals to 1, it given 120 volt and Standstill resistance is 0.25 plus 1 I have added, and 1 into 0. Sorry, standstill reactance is 1 only. Now, if you divide it, you will get a rotor current of 74.96 amperes at the starting when you have added a external resistance. Now, if you see the power factor now, I think the next question is power factor. Yeah, if you see the rotor power factor, you will see how much it is improved. Now, power factor after adding external will be resistance by impedance. Resistance is R2 plus R external divided by impedance will be R2 plus R external square plus Sx2 square total under root. Now it will be 1 plus 0.25, 1.25, 1 plus 0.25 divided by 1.25 square plus 1 square. Now if you see this, this will come around 0.78 or something. Previously we were getting a zero point 0.2. So by adding just a resistance, external resistance to the rotor, you can get a improved power factor at the starting. So this is during running conditions they will slowly remove it. That's another concept, because running power factor will always be much higher than the starting. We got the running right around zero point 0.9 or something in the previous case. So that's there. So only during starting condition we kind of require this arrangement. Okay. Now the next question is the torque starting, the torque Newton meter. So electromagnetic torque, the starting is P air gap power by 2 pi ns. So S here at the starting means S is equals to 1. Now S times power gap power is equals to rotor copper losses. So air gap power is nothing but the rotor copper losses now. But here the R2 is now added with an external resistance. So 3 I2 square R2 plus R externally have to calculate. Now rotor current we have calculated, that is 74.96 square multiplied by 1.25. It will come out to be some calculated
Yeah, please go to the previous slide where you calculated this current 74.
yeah, 74 and
Okay.
1.25 multiplied by 3. So it's 21.071 kilowatts we got here, the power. Now you have to divide it by 2 pi ns. That's, there is no change in that. 21.071 into 10 cube divided by 2 pi into 50 by 3. You can divide by 2 and 50. So it's 201.3 something Newton meter. So yeah, this is what our starting torque. How much is the starting torque in before condition? You see, yeah, here it is 97 Newton meter, but now we see the starting torque is also improved when you added the external resistance. So this is some advantages, but the entire power flow diagram, the losses, the air gap power, mechanical power, and how the uh, relations in this air gap power between mechanical rotor copper losses, and also this torque speed characteristics after adding this resistances, everything we will see even much in detail in the next week. But for today, these are the discussions which we are going to discuss for today. The main focus of today's discussion is on the equivalent circuit of induction machine. So however we have arrived at the induction machine with the concept of transformer actually. Now, transformer kind of principle, we okay, efficiency decreases. Yeah, losses will be more definitely. That's not. That's why we remove it as we run the motor. It's not suggestible also to adding a external resistance, but just to the starting to get a good torque and also improve power factor. So yeah, coming back to today's discussion, equivalent circuit we started, and the how we can arrive at the equivalent circuit with the understanding of transformer concepts we have seen, and to kind of merge these two, primary and secondary, required conditions, frequency should be same, the current should be same. So that concepts to arrive that we have assumed an imaginary motor, pretending our running motor as a standstill motor, so that my stationary observer sitting on the stator can't differentiate it which is running or imaginary, because both are having the same rotor field generated. So with that concept, we have arrived at the complete equivalent circuit of a uh, induction machine. This one, and then we discussed how the power is also being balanced in the form of mechanical and copper losses in both imaginary and the actual motor. And then we solved some problems which are direct substitution of the formulas which we have derived today. And I look forward to the next week discussion with you about the detailed part flow diagram of induction machine, and the torque speed characteristics of induction machine for different loading conditions. So if you have any doubt today, please ask me. Okay, if you come up with any kind of doubts or any confusions, please raise in the discussion forum, or else just for the next week, just keep, make a note of it, and we will discuss in the next week session. So that's all for today. Thank you for patiently attending the session and discussing concepts with me. Thank you. I'll meet you all in the next week. Thank you. Thank you, Dinesh.